All right, let's try another fluid dynamics here. It says, what is the pressure drop due to the Bernoulli effect if the water goes from a 3 centimeter diameter nozzle or into a 3 centimeter diameter nozzle from a 9 centimeter diameter fire hose while carrying a flow of 40.0 liters per second? All right, well, this would be a good time to kind of review what we did in lecture. And so if the pipe narrows, we got to get the same flow rate. So Q would equal to area times velocity. And if we call this where it starts area 1, and then it flows into some other area, area 2, then of course area 1 times velocity 1 must be the same as area 2 times velocity 2. So that was our continuity equation. The other thing we had was the energy, and it's really an energy density. We took kind of one little chunk here and said, okay, if you look at the area per, or excuse me, the energy per volume here, there would be an energy due to its kinetic motion an energy due to its gravitational energy, and then what we call the pressure at number 1. Then later on, that pressure may increase or decrease because that pressure is kind of the squeezing, so it's a stored energy there. Of course, we would also have then a kinetic energy and also a gravitational potential energy. And so if we write this kind of as a pressure 2 minus a pressure 1, and so a pressure change, then there would be a pressure change because of one reason is right here. There is a speed change, a change in the kinetic energy. And another reason would be for a height change. Now, I think in this problem, they're trying to make it really clear that this is not part of the problem, that we're not going uphill or downhill. They don't say anything about it. In fact, I kind of picture this as the end of the fire hose, where here comes the hose, and then near the end, the kind of the brass nozzle tapers off. And even if you were pointing it straight up, there wouldn't be much of a height change, but kind of imagine holding a hose horizontally here. And so that's what your author called the Benulli effect, where he calls the general Benulli effect when you got both of them going on. So I think it's fair to say there is no energy change due to height. Okay, but there is an energy change due to velocity. And if velocity number 2, and you can see here how it narrows, is more than velocity number 1, this number would give us a negative. So there's a drop in pressure. And it makes sense. We lose potential energy, and I should say pressure potential energy. Okay, so we lose pressure energy, and it becomes kinetic energy. And that's this question, at least part A, what is the pressure drop? So what I need to find then is these two different speeds. So let me use the continuity equation here and say, okay, the flow would be Q over area 1. And they made it very clear that it was 40 liters per second. And then, of course, the area would be pi, and it's going to be the radius squared. And so they said the diameter was 9. So I'm going to change that to 4.5 centimeters, and I'm going to even change that into meters. So this is the radius, 4.5 centimeters, or 0.045 meters. Now, again, that doesn't really kind of match the top here, but maybe this would be a good time to remind you of the definition of a liter. A liter is a box that is 10 centimeters by 10 centimeters by 10 centimeters. That is equal to 1 liter. So if you had a big box that was a cubic meter, like that, you would take and you would put a box, say, here. And I don't know if my picture's going to show it, but how many times can you fit 10 centimeters into 1 meter? And there's 10 of them. 3, 4, 5, 6, 7, 8, 9, 10. And so forgive my drawing not being equally spaced, but you're going to put 10 across here. And in a vertical, there's going to be another 10. 2, 3, 4, 5, 6, 7, 8, 9, 10. And in a depth, there's going to be another 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is a mental way of trying to say that a cubic meter would be fitting 1,000 of these little things, because I'd go 10 across, 10 high, and 10 deep. And so 1,000 liters must be in 1 cubic meter. So there's the unit conversion. Let me jump over to another page here. Okay, so velocity number 1 then would be, and what I'm going to do is change this to 1,000 liters per cubic meter. So I'm going to divide that by 1,000. So it would be 0.040 cubic meters per second. That would be the flow rate. Divided by pi times 0.045 meters squared. And now you're going to see how cubic meter and square meter leave you with meters per second. So there's the velocity, at least at number 1, or before it gets sped up through the narrow nozzle. So 0.04, and then divided by a pi, and also divided by a 0.045 squared, gives me a velocity of about 6.29 meters per second. So again, there's the flow coming through the hose there. Okay, now velocity number 2 would be the same flow rate, but now we got to squeeze it. So coming over here, and it narrows down, and so again, same flow rate. But the area is pi r squared, and in this case, let me just check here. They said the diameter is 3 centimeters. So half of that for the radius is 1.5 centimeters, and then move the decimal 2 places for a meter. Okay, so to get the flow rate in meters per second, let's see what I get. So 0.04 divided by a pi, divided by a 0.015 squared. And so I get a flow rate of 56.6 meters per second. So clearly a huge speed up. And again, we know that because we got to get the same amount of water through. So it's got to go faster at point number 2. So really fast over here or here. And actually, it's pretty fast over here too, but it's even more so coming out the end of the nozzle. Okay, so now we can come over here and see if we can calculate this pressure drop. And so pressure 2 minus pressure 1 is 1/2 rho V1 squared minus V2 squared. 1/2. And the density of water, we'll have to look that up, but it should be 1,000 kilograms per cubic meter. So then when I put in the velocity at number 1, which is 6.29 meters per second, and I square that, and then I minus the 56.6 meters per second and square that, I will get a number. Let me focus also on the unit, though, because when I square this, I'm going to get meters squared over seconds squared. And if I go ahead and take this meters squared, but only cancel one of them down here, so that'll still be a meter squared, I will have kilogram meters per second, and that's a Newton. And since I only canceled off one, I still have a square meter. So this would be Newton per square meter, and that's Pascal. And that's what I was after. I was after putting these in the base units, knowing that the pressure drop would come in as pascals. And clearly this negative one is bigger than here, so we're going to have a negative. In fact, I'll just do this number first. 6.29 squared minus 56.6 squared. So there's the negative number, then times 1,000. So last answer times 1,000, and then times 1/2. So this would be a pressure drop of 1.58 times 10 to the 1, 2, 3, 4, 5, 6. So about a 1.5 million pascals in drop. So I'll put a negative there. Okay. And so I guess that's the answer to A. Because B then says, to what maximum height above the nozzle can the water now shoot? So now it's going really fast, as you see here. And so if you were pointing the nozzle just straight up, how high would it go? Now, again, as a fire hose, you probably have a little angle to it so it arches up. But you can imagine at this speed, it's going to go pretty high. And maybe I'll just go all the way back to kinematic equation number 3. Because if we have initial and final speeds and the acceleration, we can figure out how high it goes. And we do. So water going up here and getting to its maximum, its final speed at the top would be 0. Coming out of the nozzle is the 56.6 meters per second. The acceleration is a negative 9.8. And then we're going to get the change in the height. And so because it's height, let me put a delta y. And so now I can solve for how high does it go. So 56.6 squared, and moving it to the other side would be a negative, canceling with that negative. Then dividing by a 2 and dividing by a 9.8 is going to give me an enormously high height of 163 meters. So assuming we have enough pressure here to do this dropping down and getting the speeds, and so a fire hydrant will have this, it'll shoot the water extremely high if that's what you needed to put out a fire. Now, I suppose in real life it's going to be a lot less than that for a couple of reasons. One, there is a little viscosity, and that's kind of minor compared to the air resistance as it goes up here, and it's got to push against the air, and so air resistance is going to make it way lower. So both viscosity and air resistance is going to keep it way low. But even if it goes 1,000 meters, that's pretty high. You can shoot water up into a window of a burning building, and I think that's kind of a good point of this problem. All right, hopefully that helps a little bit with your fluid dynamics. Take care.